Good morning all. We are going to study about some losses in DC machine. So there are various types of losses occurring in different parts of DC machine. All of them causes heating. Mainly the heat generated by these losses has two major serious effects. Increase in temperature of machine, which affects the performance and life of the machine, particularly insulation. Hence the rating of machine directly affected by the losses. And also by producing heat, wastage of power, which reduces the efficiency and increases the operating cost. So these are the main disadvantages of heat generated by these losses. And the cost of energy wasted in the form of heat is very important, particularly for large industrial motors where large power is required. In large machines, the operational costs become higher when these losses are higher. So, however, temperature rise due to losses is an important issue for large as well as small machines because it affects the performance and life of machine. If it is either small or large machine, these losses will affect performance and lifespan of machine. So, losses cannot be eliminated completely. We know that losses we cannot eliminate it completely but can be reduced by proper design of machine. Therefore, the initial cost of machine is greatly affected by losses. So, there are mainly four types of losses are there. Various losses occurring in DC machine can be subdivided into electrical or copper losses, that is present in windings. We know that in a DC generator there will be armature winding and also field winding. So there will be field winding copper losses and armature winding copper losses. We represent it as I square R losses. And another one is magnetic losses, that is iron or core losses. We have studied iron losses in transformers as hysteresis loss and eddy current loss. The same losses will be present in this generator also. And mechanical losses, which is due to the rotational part coming in DC machine, there will be friction and windage losses. That is called as mechanical losses. And some losses which are difficult to calculate or determine are coming under stray losses. Okay. We will study this in detail. First one, electrical losses. So these losses, these are known as copper losses or winding losses and ohmic losses. So electrical losses is also called as copper losses, winding losses or ohmic losses or I square R loss. All are actually electrical losses. And these losses occur in the winding due to the flow of current through them. Okay. First one is armature copper loss. We represent it as Ia square Ra, where Ra is the resistance of armature, interpoles and compensating winding, and Ia is the current through the armature. Therefore, this loss is variable and depends on the load on the machine, because we know that load increase ചെയ്യുന്നതിനനുസരിച്ച് armature current increase ചെയ്യും. So, armature copper loss is a variable loss. Okay. When we increase the load, the current produced in the armature also increases. So, armature copper loss is a variable loss. Next one is field copper loss. In shunt generator, it is we have studied the different types of generators. Self-excited generators are of shunt wound and series wound and compound wound generator. In shunt generator, this field winding resistance, field winding resistance is represented as ISH square RSH, or we call it as VIH, and it is practically constant. We know that the shunt field current is almost constant. We consider this shunt field current is constant, so this loss is considered as a constant loss. In series generator, it is represented as the field loss is represented as field copper losses I series square R series. But we know that in a series generator, armature and the series field winding are connected in series. So all the armature current which flows through the same as series winding current. So armature current is a variable current, so series current is also variable according to the based on our load. So I series is a variable term, so it's a variable load, variable loss. So shunt field copper loss is constant loss, but series field copper loss is variable loss. Okay. Now another loss is magnetic losses. Magnetic iron or core losses. We have already studied there are two types of iron losses, hysteresis loss and eddy current loss. Hysteresis loss. That's what we studied. Hysteresis loss. This loss occurs due to reversal of magnetization. The core undergoes one complete cycle of magnetic reversal after passing through one pair of poles. First it is magnetized and then it is demagnetized. Okay, but we can see this mantle-field intensity, mantle-flux density will be lags behind the mantle-field intensity. Be lags behind edge like this. When it is magnetized, and it approaches the maximum or saturated point, then when the magnet is demagnetized, it goes through a path not as the initial path, it lagging behind it. So this loop is known as hysteresis loop. The core undergoes one complete cycle of magnetic reversal after passing through one pair of poles, that is north and south pole. Hysteresis loss is given by Steinmann's formula. We have already studied WH is equal to KH Bm raised to 1.6 FV watts, where KH is it's a hysteresis coefficient and Bm is the magnetic flux density, maximum flux density, F is the frequency of magnetic reversal in cycles per second, and V is the volume of core. Okay, and the area of this loop gives the loss, hysteresis loss. Then next is eddy current loss. Okay, eddy current loss is when the armature core rotates, it cuts the magnetic flux, hence an EMF is induced in the core also. This induced EMF circulates a large current in the core as its resistance is small. So this current is known as eddy current. Okay. So the loss of power due to this circulation of eddy current through the core is known as eddy current loss. We know that it is an unwanted current which is circulating through the core. Okay. So that current is known as leakage current or eddy current. Okay. The loss due to this current is known as eddy current loss. If solid iron core is used, like this, if a solid iron core is used, this loss can be very high and the core will be get heated. In order to reduce this loss, the core is built up of thin laminations like this. By using these thin laminations and insulated from each other by a thin coating of varnish or mica, and each lamination of thickness 0.3 to 0.5 mm, then we can reduce our eddy current. So hence the magnitude of eddy current is reduced considerably, thereby reducing eddy current loss also. Okay. And to reduce hysteresis loss, we know that we use different type of materials which have less hysteresis losses. In order to use cast iron, we use cast steel to reduce hysteresis losses. Okay, and to reduce eddy current losses, we laminate the core. So the equation for eddy current losses, WE is equal to KE Bm square F square T square V watts, and KE is the constant, eddy current constant, and Bm is the maximum flux density, F is frequency, and T is thickness of lamination, V is the volume of core. We have already studied in transformer the same losses are the iron losses coming in DC machine also. Okay, then mechanical losses. Mechanical losses means These are the losses produced due to friction and windage. Friction with the air is known as windage loss and which is caused by rotation of machine. These losses are depend on the speed of machine. These losses, mechanical losses are depend on speed of the machine. Friction loss depends on the type of bearing, which depends on type of bearing used and on the viscosity of the lubricant. Brush friction loss depends on the contact area and brush pressure. It also depends on the factors like material of brush and commutator, their polish condition, etc. Okay, so windage losses are caused by the air moving around the armature, and the ventilation losses are also a part of windage loss. It is produced due to fan provided for cooling for the machine. Okay, so these are the mechanical losses. Then another one is stray losses. Stray loss is losses which cannot be considered as electrical or magnetic or iron or mechanical losses. So some losses which will be present in the DC machine which are not can be considered as an electrical loss or a magnetic loss or mechanical loss or collectively called as stray losses. These losses are very small in value and therefore they are very difficult to calculate. Stray losses are generally neglected in small machines. For a large machine, they are generally considered to be 1% of the total output power. And these losses mainly include additional core loss because of distortion of flux due to armature reaction. We are going to study this term armature reaction, what it is, and these losses coming by additional core loss because of distortion of flux due to armature reaction and copper loss due to short-circuited coil during commutation and the copper loss due to non-uniform uh, distribution of current in armature conductors. These are the main reasons for stray losses. Additional core loss because of distortion of flux due to armature reaction and also copper loss due to short-circuited coil during commutation and also non-uniform distribution of current in armature conductors. So these are very difficult to find out these losses. So usually in small machine we neglect this loss. And mainly these losses are classified into two, that is constant and variable losses. Constant losses are those which remain constant irrespective of the load conditions. Mechanical losses, core loss and shunt field winding copper losses are included in constant losses. Okay, and variable losses are those which increase as the load on the machine is increased, and these are armature copper loss, series field winding copper loss and interpole and compensating winding copper losses and brush contact power loss. These are variable losses coming under variable losses. Okay, and I just summarize our total losses into this topic. Losses mainly classified into one second. Losses are mainly classified into copper loss, iron loss, mechanical loss and stray loss, in which copper losses are of three types: armature copper loss including interpole, compensating winding and brush contact resistance, and all these losses are coming under variable losses. And series field, next one is series field winding copper loss and shunt field winding copper loss. So these losses are coming on the windings. These losses are present in windings, copper losses. Okay, due to the winding resistance. And these losses are variable losses. And next one is iron loss, which is present in core of the DC machine. And these are mainly hysteresis loss and eddy current loss. And we consider this as a constant loss. Iron losses are constant. Next one is mechanical losses. This is due to the rotational part in the DC machine and which are mainly classified as frictional loss and windage losses, and these losses are constant. And some losses which are not coming under these categories are called as stray losses, which is very small and also it is difficult to find out or determine. So these losses are collectively called as stray losses. Okay. Then now we are going to study the power stages of a DC machine. Before going to the power stages, first we explain what is a generator action. Okay. We know that in a DC generator, the input given as a mechanical power input. So when the machine is operating as a generator, it is driven by a prime mover. So we give a mechanical input to the shaft. So there will be a torque. Let the input torque be taken it as T in. It is denoted here T in. Okay. So we are going to rotate the armature. So the mechanical input power is given through the prime mover. So let's assume the torque input torque is T in, and the corresponding input power, we know that power and torque relation P is equal to 2 pi n T. So P in is equal to 2 pi n T in, where n is speed in RPS. Okay. Thus, it develops what happens when a prime mover gives a rotation to the armature starts rotating and the armature winding cuts the magnetic flux and it induces an EMF in the armature winding. So, the induced EMF is EG, and which circulates a current through this armature winding, that is armature current IA. And due to this circulating current, we know that this winding is a closed circuit and armature current will be produced in the armature winding. So now it becomes a motor in action, that is when a current carrying conductor placed in a magnetic field, it experiences a force and this force collectively produces a torque in it. So there will be another torque, that is counter torque produced in the armature due to this armature current. നമുക്കറിയാം ഒരു കറന്റ് ക്യാരിങ് കണ്ടക്ടറിനെ ഒരു മാഗ്നറ്റിക് ഫീൽഡിൽ പ്ലേസ് ചെയ്ത് കഴിഞ്ഞാൽ അതിനകത്തൊരു ടോർക്ക് പ്രൊഡ്യൂസ് ചെയ്യും. ദാറ്റ് ടോർക്ക് ഇസ് എൻ ഓപ്പോസിറ്റ് ടോർക്ക് വിച്ച് ഇസ് പ്രൊഡ്യൂസ്ഡ് വിച്ച് ഒപ്പോസസ് ദ കോസ് വിച്ച് പ്രൊഡ്യൂസസ് ഇറ്റ്. ഇങ്ങനെ ഒരു ടോർക്ക് പ്രൊഡ്യൂസ് ചെയ്യാനുള്ള റീസൺ എന്താണ്? ദാറ്റ് ഈസ് ഇൻപുട്ട് ടോർക്ക്. സോ ദിസ് ടി എ വിൽ ബി ഓപ്പോസിറ്റ് ടു വാട്ട് ടി ഇൻ ആയിരിക്കും. സോ according to Lenz's law, we know that any change will opposes the cause which produces it in that machine. So due to motor action, torque TA is produced in armature which is opposite to the input torque. According to Lenz's law, this is known as counter torque. TA is a counter torque. So the work done by the prime mover in overcoming this counter torque is converted into electrical energy. So armature current produce ചെയ്യുന്ന torque ഓവർകം ചെയ്യാൻ വേണ്ടി ഒരു വർക്ക് ഡൺ വരും. പ്രൈം മൂവർ ചെയ്യുന്ന ഈ വർക്ക് ഡൺ ആണ് മെക്കാനിക്കൽ എനർജിനെ ഇലക്ട്രിക്കൽ എനർജി ആയിട്ട് കൺവേർട്ട് ചെയ്യുന്നത്. സോ ദ ഇലക്ട്രിക്കൽ പവർ ഡെവലപ്ഡ് ഇൻ ആർമേച്ചർ വി ക്യാൻ റൈറ്റ് ഇറ്റ് ആസ് PA is equal to 2 pi n TA, and also it can be represented as PA is equal to the EMF induced in that generator is EG and the current produced is IA. So EG into IA is also the power, electrical power developed in armature. Okay. Then now we can represent this power stages of this DC generator. We know that the power mechanical power is converted into electrical power. So we know that when the prime mover gives the input torque to the armature, so mechanical input is given to the DC machine. So the mechanical power input can be represented as P in is equal to 2 pi n T in. Okay. So this mechanical input, we know that by producing this counter torque, the work done to overcome this counter torque, this prime mover will convert the mechanical energy into electrical energy. So electrical power is developed in armature. But this electrical power developed in armature is not equal to our mechanical input. There will be some power will be wasted as heat during this operation. When it converts mechanical energy into electrical energy, some of this power is wasted as heat energy due to friction and windage losses, and also there will be some losses present in the core of the DC machine, that is we call it as iron losses. So iron, friction and windage losses are occurring during the process of converting mechanical power into electrical power. So we can call it as when mechanical input power is given, input power is converted into electrical power. At that time, some of the power is wasted as losses, that is iron, friction and windage losses. So PA is equal to Eg into Ia is the electrical power developed in armature, and which is also represented as in terms of torque 2 pi n PA. And this this electrical power developed in this armature will be taken as the electrical output, but it will not be equal to the electrical output taken across these 2 points, because there will be some losses in the winding. There will be a winding resistance present in armature and also winding resistance present in the field winding. So we have to consider these copper losses also. So some of this power will be lost as copper losses, and the remaining will be collected as the electrical output power. And the electrical output power can be represented as P output is equal to terminal voltage V into load current IL. So electrical power output is V into IL. Okay. So we are giving mechanical power input. A portion of this mechanical power input goes as iron, friction and windage losses. The remaining part is converted into electrical power developed in armature, which is Eg into Ia, and a part of this electrical power goes as copper losses, that is armature and field copper losses, and the remaining portion is collected as electrical power output. Okay. Now we can study some efficiencies present in DC machine. Okay. So we have studied our different power stages. This will be very useful for calculating the efficiency and also losses by using this power stages. Okay. So there are different efficiency. First, we know that the mechanical input is converted into electrical power. So the first one is mechanical efficiency. It is represented as eta m, that is, this one is A. Power stages we can represent it as A, B, C. Okay. So V by A is mechanical efficiency. That means electrical power developed in armature divided by mechanical power input. So we can represent it as PA by P in. And we know the equation PA is Eg into Ia divided by P in, input power. So electrical power developed divided by mechanical power input is mechanical efficiency of the DC machine. And next efficiency is electrical efficiency. Electrical efficiency is in the power stage C divided by B, that is C by B, and which is known as electrical power output divided by electrical power developed in armature. So we can represent it as P out divided by PA. We know the equation VIL divided by EGIA is electrical efficiency. So electrical power output by electrical power developed is electrical efficiency. And the overall efficiency of a DC machine, or which is also known as commercial efficiency, that is represented as eta E. Eta O is represented C by A, which is C by A, the power stage C by A, that is electrical power output divided by mechanical power input, P out divided by P in. So if there is no just concern. If it is not given us find out mechanical efficiency or electrical efficiency, generally we calculate the efficiency of a DC machine as overall efficiency. Okay. Last, electrical output divided by mechanical power input ആയിട്ടാണ് നമ്മൾ അത് ഒരു മെഷീന്റെ എഫിഷ്യൻസി കാൽക്കുലേറ്റ് ചെയ്യുക. ഓവറോൾ എഫിഷ്യൻസിയാണ് നമ്മൾ ജനറലി കാൽക്കുലേറ്റ് ചെയ്യുക. In the question, if it is specified that find out the mechanical efficiency, then only you have to find out it by efficiency by this equation, electrical power developed by mechanical power input. Okay. So overall efficiency is VL by power input. So these are the different efficiencies coming in DC machines. Next is condition for maximum efficiency. There will be some condition for maximum efficiency. Let us consider a DC shunt generator with a terminal voltage of V volt and load current IL. Okay, V and the load current IL. Okay, then the power output. We know that the efficiency equation in output by input ആണ്. നമുക്ക് ആദ്യം ഔട്ട്പുട്ടിന്റെ ഇക്വേഷൻ എഴുതാം. The power output is V into IL. For a DC shunt generator, we consider the power output is V into IL. Now, input കിട്ടണമെങ്കിൽ എന്തൊക്കെ അറിയണം? Output plus losses അറിയണം. Now we get the equation for output, V into IL. Now we are going to find out the variable and constant losses. Variable losses is armature copper loss, Ia square Ra, and we can represent it as IL plus ISH. Ia, which is sum of shunt field current plus load current. So we can represent it as IL plus ISH whole square Ra. We know that shunt field current is very small as compared to the load current IL. So we neglect it, and variable loss we can write it as armature copper loss IL square Ra. Okay. Let constant losses including shunt field copper losses also. Okay. That is WC. We represent it as constant losses. We represent it as WC. Now we can write the equation for efficiency. Here you can see input power. Now we can write the equation for input power. We know the output power as V into IL plus constant losses plus variable losses will give you the input power. So we can write the equation P in as V into IL plus WC, constant loss plus IL square Ra. So what is the equation for efficiency? Output V into IL divided by this equation for input. Substitute the equation V into IL plus WC plus IL square R. This is the equation for efficiency. Now we are going to find out the condition for maximum efficiency. Condition for maximum efficiency കണ്ടുപിടിക്കാൻ വേണ്ടി നമ്മൾ ഇതിനെ ഒന്ന് rearrange ചെയ്യാം. Efficiency equation. Just divide numerator and denominator throughout by this V into IL. So V into IL ഒന്ന് throughout divide ചെയ്യാം. VIL and also throughout divided by VIL. Okay. So what will you get? The numerator will become 1 and denominator 1 plus WC by VIL and ILRA by V. This will be the efficiency equation. Now if we are going to find out the condition for maximum efficiency. How can you find out the maximum efficiency? We know that in this equation, if we reduce this to minimum value, efficiency will be maximum. So efficiency will be maximum when the denominator is minimum. So normally നമ്മൾ mathematics പഠിച്ചിട്ടുണ്ട്, to find out the maximum value, just differentiate with respect to that variable in that equation and equate it to 0. So just divide this denominator with respect to just differentiate this denominator with respect to IL, because in this equation voltage IL load current ആണ് variable ആയിട്ട് വരുന്നത്. So just differentiate that equation with respect to IL. D by DIL ആണ് ചെയ്യേണ്ടത്. Differentiate with respect to IL because it is the variable coming in this denominator. So just take the denominator and equate it to 0. Okay. So D by DIL of 1 plus WC by VIL plus ILRA by V equal to 0 കൊടുക്കുക. Then by differentiating this equation, you will get d by dl of 1, 0, d by dl of this value, and the 1 differentiate d by dl of 1 by il എന്ന് പറഞ്ഞാൽ എന്താ വരിക, which is equal to minus 1 by il square വരും അല്ലേ. So in this term, Wc by V is constant, so Wc by V into IL square minus Wc by V into IL square എന്ന് കിട്ടും ഈ ഒരു ടേമിനെ ഡിഫറൻഷിയേറ്റ് ചെയ്യുമ്പോൾ. Now differentiate this term IL RA by V. d by dl of IL is 1, so the constant RA by V is the result. So we can write the equation as Wc by VI IL square plus RA by V equal to 0. Now ഇതിനെ നമ്മൾ ഈ ഇക്വേഷന്റെ ഈ ഒരു ടേമിനെ റൈറ്റ് സൈഡിലോട്ട് എടുക്കുക. സോ RA by V is equal to WC by VIL square എന്ന് കിട്ടും. So from this V and V get cancelled. So IL square RA is equal to WC. This is the condition for maximum efficiency. So from this equation, you can find that efficiency will be maximum when the variable losses are equal to constant losses. Okay. So load current corresponding to maximum efficiency is given by, from this equation, just find out the load current at maximum efficiency condition, that is IL is equal to root of WC by RM. The condition for maximum efficiency in variable losses are equal to constant losses when the condition is okay. And when we consider the variation of efficiency with the load current, when we draw a load current characteristics with respect to efficiency, when the load current increases the efficiency of machine increases up to a particular value. The efficiency of machine increases with the increase in load. Efficiency is maximum at a particular point or particular value of load current where variable loss is equal to constant loss. So variable loss is equal to constant loss ആവുന്ന കണ്ടീഷനിലാണ് efficiency maximum ആയിട്ട് കിട്ടുക. And if the load current increases further, this efficiency starts decreasing. And the machine, so these machines are generally designed to give maximum efficiency at or near at the rated output of the machine or near to the rated output of machine. So നമുക്കറിയാം വേരിയബിൾ ലോസ് ഇസ് ഈക്വൽ ടു കോൺസ്റ്റന്റ് ലോസ് ആവുന്ന കണ്ടീഷനിലാണ് മാക്സിമം എഫിഷ്യൻസി കിട്ടുക. അപ്പോൾ ഒരു റേറ്റഡ് ഔട്ട്പുട്ട് എന്ന് പറയുന്നത്, റേറ്റഡ് പവർ ഔട്ട്പുട്ട് എന്ന് പറയുന്നത് നമ്മൾ ഡിസൈൻ ചെയ്യുക നോർമലി മാക്സിമം എഫിഷ്യൻസി കിട്ടുന്ന രീതിയിലാണ്. അതായത് നിയർ ടു റേറ്റഡ് ഔട്ട്പുട്ടിനോ അല്ലെങ്കിൽ അറ്റ് റേറ്റഡ് ഔട്ട്പുട്ടിലോ ആയിരിക്കും നമുക്ക് മാക്സിമം എഫിഷ്യൻസി കിട്ടുക എന്ന രീതിയിലാണ് നമ്മൾ മെഷീനെ ഡിസൈൻ ചെയ്യുക. Because then only you will get higher efficiency and also operational cost can be reduced at maximum efficiency. So when we get the maximum efficiency, operational cost will be less. Okay. So these are the topic today. Thank you.